Hey YouTube, JP Dillon. We hit 1,000 subscribers last night, and I'd like to thank all of you for tuning into the channel and subscribing and sending it to your friends, etc., and kind of keeping this going. I know it's not the most frequently updated channel on YouTube, and I do apologize for that. Sometimes life just gets in the way. I have lots of interesting stuff to work on, just very little time. So I try to make use of time here at work and use customer machines as things to portray for repair. What we have today is a Yamaha R-300, circa 1982-83. And it had a blown STK 2030, which we replaced. And also the voltage amplifier, which is the little STK 3042 Mark II, was also bad. Now, I replaced both, fired the setup, and it immediately smoked. The left channel began to oscillate like crazy. It was literally about 80 volts peak to peak at about 400 kilohertz, so it just immediately blew the fuse and died. This is the problem I'm seeing with a lot of STKs that are of modern manufacture, is that they're just, the quality control is no good. So I called the customer up, and he had seen the video on the CR400 I did with the little modules, the TDA7293 based modules you can get from Parts Express. And so we're going to do that modification on this. Now the CR400 is a little bit different because they have a different amplifier design. So we're going to have to tap the signal a little bit further back in the machine. But this is what you get when you get the two modules. You can see they're really simple. All it is a 7293 mounted on a board with a soft start circuit, a couple of capacitors, and you've got your power supply input here, your signal input here, and your speaker output here. And so what we're going to do is mount these on the heatsink here and wire them up so that they work. So the first thing we'll have to do is pull the heatsink to make it easier. We're also going to pull the driver IC, because the signal input here is where we're going to steal it from, because these will accept a preamp line level signal, which is going to go into the input pins on the STK 3042 Mark II. So let's get cracking. What we'll do, we'll make a mark for the regulator and disconnect this, unsolder the devices, pull the devices out, and then we'll take a look at the architecture and see where I'm going to be taking power signal from, and obviously we're going to put the output at the emitter resistors down here at the output of the emitter resistor, just before the RC networks. So let's flip this thing over and get cracking. Alright, so here's our work area. Let's get our solder wick and a soldering iron. And let's start by taking out the IC. The best solder wick I've found to use is this Chemwick rosin. Not cheap. You can find it on the internet for a pretty good price. But most dealers want about 15 bucks for that roll. But it's the best one out there that I've found. There's plenty of rosin. The braid is well saturated and wicks it up very quickly, so you can limit the amount of time that the heat is on the particular lead. Really doesn't matter here since we're taking this one out to discard it, but just a little FYI for you. And as an iron, I absolutely love this old Hakko 930. I think they're up to the 936 now. I've been using this for over a decade, and I like it. Okay, so we're just going to make sure all the excess solder's off. That's the driver device there. I got to trim my solder wick so I have some fresh wick for the main amplifier IC. And as I mentioned before in my previous video, these are really easy to wire up because all you need is power supply, signal in, and signal out, which can be easily adapted to one of these things. Make sure to check your schematics, because the R-300 uses plus and minus 35 volts, which is about at the limit that these Parts Express modules are good for. The TDA7293 itself, I believe, is rated to plus and minus 50 volts, but that's pushing it, and then you definitely wouldn't have the overhead for the 4-ohm load. I don't know, I could look into making my own, but this is just so much easier and cheaper, as many things from China are. But the STK-based amplifiers, there aren't a lot of people that are making really good, legitimate ones, so it's becoming increasingly difficult. Alright, so we got them unsoldered. Let's pull them out. There's your driver IC. And let's make a little mark on the regulator here. Unplug that. And let's pull out the heatsink with the STK on it. And then we'll work on figuring out how to mount these things, which would be fairly easy actually, because we've already got mounting screws. That just comes right out. There's the old heatsink module. Since we already have emitter resistors on the new modules, I'll probably just end up pulling those out, and then the output of the speaker here will go to right above the RC networks here at the center tap of the dual emitter resistors currently there. So let's take those out. And these little buggers, these are the emitter resistors. I'd love to play music for you guys or something, but then I'd get nailed for copyright claim. And then they'd kill all the audio to the video, and this video would be absolutely useless because I like to narrate a lot of what I do. Otherwise, if you're just a layman or something, you're probably just going to sit there and stare and go, what the hell is he doing? I can't hear anything. He's just doing a bunch of crap here. What is this stuff? So, but it's all because artists need money too, and apparently large forms of social media networking are a great source of revenue, which makes sense. Alright, let's pull these out. Okay, wiggle, wiggle. So, this is a dual emitter device. So there was in the STK device, there was an emitter transistor or emitter output here and emitter output here, and then this is the output that goes to the speaker relay. So that's where we're going to attach the output of the amplifier module. I'm just going to make a little circle here. So if you guys want to attempt this with your R-300, you can. So now that we have this part done, we need to figure out how to mount the devices to the heatsink. Now, just looking at this, let's see if I can center this to a point where you can see it a little bit better. Just looking at this, we've already got 2 screw holes. So, just as a mock-up, really all we have to worry about is vertical clearances to the bottom, because the heatsink mounts to the flat of the chassis on the bottom. So let's take this up a little bit. And let's take the old STK off and clean off all the heatsink goo. And then we can kind of mount it a little bit better. Alright, so there's our mounting surface. And you can see that it's not possible to mount it this way or this way, because obviously we have size constraints. They're not both going to fit there. Now if we mount them this way, we have to change the mounting holes because, well, obviously you're going to run out of space. If you just center them at the holes here, well, there's not to say that we can't flip the, no, we can't flip it over, because then the regulator will bump into the ground. Alright, so the way that we're going to do this, if I can do this, let's just do a mock-up. That's probably how it's going to end up being. Just like that. Obviously the other thing we can do is drill new holes. I don't know if I like the cockamamie weird squiggly look. Or we could just drill new holes. It is aluminum, it's easy to drill. And then we can have it a little more symmetrical. Just a little. Or we could mount them both this way, mirrored, same rather than mirrored. Yeah, I could use the original holes, but I don't like the way that turns out. So that's kind of how it will look, like that. But then I have the problem of this. I got a little bit of space underneath, but that's going to crowd the speaker wiring, because I only have about maybe that much space underneath it before I hit to the chassis for the wiring. And I could do it this way, but then again wiring runs into this. Or I could stagger them. Ooh, stagger. Meh. The problem with staggering is now I have a concentration of heat here in the center versus mounting it towards the outside like this, where there is a better distribution of heat, less concentration of heat. That may be the better thing to do. Yeah, maybe just run them this way like this. This is really the hard part, because you don't want to just mount them on there. You want to think about things like thermodynamics and heat transfer and all this extra crap that nobody ever thinks about. And this is really going to mean the difference between whether this thing survives another 10 years down the road or whether it's just going to blow up again. Now I think that this is the best setup, the best equal distribution of heat. May not be as convenient as I'd like it to be, but it will work. So this is how we'll mock it up. And I'm just going to make little marks here to drill the holes. And then we'll drill the holes out. So let's get a drill. Okay, so let's drill these things out. Just take your time with it. You don't have to rush it. Let gravity do its thing. Okay, let's just get the metal shavings off of here so we get a little bit cleaner place to work. You'll need these TO3P type Michael insulators. Okay, so we got to remember that this is the upside. If we don't remember that, we're going to run into problems mounting these things. Get all this yucky heatsink goo off. I'm going to use the old screws to drill and tap. Oh, that's the old hole. Whoopsie. I wonder why that was so easy. Use these to tap some threads. I'm using a 3/32 drill bit. Most of the self-tapping Japanese screws will be of that size. Okay, so we got that done. Now I'll need shorter screws to mount the things on. So let's get our little drawer of screws here. Let's see, we've got one there. And one there. Looks about right. Okay, the next thing we want to do is put some heatsink compound on our first module, which I'm just going to slather on here. And then we'll set down our mica insulator on top of it. And then put another layer of heatsink goo on top of that. So you've got a nice white on both sides. And let's just put the thing down here, stick it to the heatsink, and let's get our screw in there. Now, this would be a good time to put Loctite on your screw so that it doesn't back out during thermal cycling. Let's do that. You can use Loctite, you can use 3-bond, which is what most of the service tech centers have. And then we'll just run the screw down. This is aluminum, so don't make it crazy tight. Oh, yes, I'm forgetting one important thing. We need transistor hardware because that header has voltage on it, and if I just screw it down into the aluminum, it's going to blow the fuse. So, now what we need to do is find some appropriate transistor hardware, which I happen to have a box of. And all we're looking for is an insulator that the screw will go through. Okay, let's see if this will work. Alright, now let's see, using a meter, if the header is at the same potential as the heatsink, which would be very bad. So we're going to prop that up there, touch the heatsink, touch the header. See how the screw has the potential, but the header does not? That's what you want. Alright, let's get the other one mounted. Again, applying your heatsink goo, and then we'll put our mica insulator on. And apply more heatsink goo. You don't want to be able to see through the mica insulator. Just coat it so that it's nice and white. And then we'll put this one down like so. Let's find our appropriate piece of transistor hardware. This looks like it'll work. We'll see in a moment. You can put your Loctite on your screw if you'd like. I recommend it. Helps to have a magnetic screwdriver to hold everything. We're going to pass the screw through the insulative washer. And then we're going to stick this down into the device. And again, don't crank it down. Just get it tight so that it doesn't move. That's all you're after. Okay, now let's grab our meter again and see if the header is off of the heatsink. Yes, it is. So the header is isolated from the heatsink. Alright. Now we need to take a look at the machine and see what's going to be required to wire it up and where all of our attachment points are going to be. So here we are. We've got our modules mounted up. Everything seems to be happy there. They conveniently label the ground and the output there so you can see. I think what I'm going to do is color the ground side black so I know which one is ground, because otherwise I'll forget. That's a ground, that's a ground, and same with our input side. That's a ground, and that's a ground. And then with the power supply, center is ground, center is ground. And I really need to find a red one too so that I can denote the positive. Let me go get a red Sharpie. And let's see, this is the positive. Okie dokie. So that's done. So now that we've got the modules mounted to the heat sinks, the next thing I want to do is put the machine back up here and see how it's going to fit, because that's obviously important. Doesn't matter how you mock it up if it doesn't fit in the machine, right? Okay, so there's our Yamaha. Trying to make this more visible for you guys. Let's see. So we're running into an impediment. I don't know if you guys can see that, but these capacitors down here, it bumps into. Let's see if we can just flatten those out. I doubt that will really help me, but we can try. No. Those need to be relocated in order for this to fit right. Those capacitors will need to be relocated. But we can do that. That's not hard. And otherwise it fits. I mean, that's really the only point of obstruction for those two capacitors there. If I mount this up here, just taking a look down inside, nothing is obstructing on this side. That's all clear. It's just those two capacitors there. And these two resistors are close, but not close enough to be concerned. Maybe I'll just pull them over a little bit. That actually works out pretty well. So we'll move those two capacitors to the underside of the machine. They're not particularly high profile or very significantly important. And it's just under the machine here. If we take a look, that's them right there. We got one right here, and we got one right here. So let's just desolder those and take them out. I hope this just didn't flip my video. We'll find out in a moment. Okay. We'll just take these guys out. And then we'll relocate the caps. Okay, so now we've relocated those capacitors to the bottom of the machine and reinserting the heatsink. There is now no obstruction for any of the components, so this fits in here now. So what we'll do is now we have to figure out where to steal the signal from and stuff and wire it all up. And then we can go about testing it once we get it wired up. So that'll be the next step. And what I need is to figure out where the power supply voltages are and what pins for the output devices. Obviously we know what the output pins are. We need to figure out the power supply pins and the input pins here for this, which is either going to require a schematic for the machine or for the device, the 3042 Mark II, both of which is possible. So the next thing to do is to trace out where the power supply voltages come from. It's going to be on one of these pins. Very likely with these large jumpers here, probably on one of those, but we can check that. So let's get to it. So I'm not sure if you guys can see this. You probably can't. Well, they have marks, plus and minus, for the capacitors. Now, the way that you can tell what is ground, usually in a dual rail supply, the ground is where two legs of the capacitors are tied together, and then the transformer center tap goes to that. So in this case, this and this are the ground, which are unified, and then you've got this, which is your minus supply voltage, and this up here, which is your positive supply voltage. So then what you want to do is take your meter, and we're just going to do a continuity check. And what we're going to do is figure out which one of these pins is the positive and which one's the negative supply. So first we're going to do the negative down here. Okay, so it looks like pin 6 is your negative supply. So let's just write a little note on the bottom here. B minus is 6. And let's check the positive supply. That charges up. Let's see, we got 6, 7, 8, and 9 are blank, 10, 11, 12, 13, 14, 15. Looks like pin 15 is the positive rail. So let's make our other note. B plus is 15. And now we need to find our ground. and it looks like pin 2 is our ground, just because it's the fattest foil trace next to it. Yeah, pin 2 is the ground pin for everything. Now I know what you're thinking, why not just run wires directly from the capacitors in the chassis to the modules? You can, but then you'll usually get ground loops, because the distance of the rails and the distance of the ground to the modules are different lengths. You want to try to keep everything localized to the original spot where the SDK device soldered in, to avoid any sort of ground loop hum or anything like that that could be a detriment to the sound. You want this to be hi-fi, you want to keep everything localized. Now, as far as the signal, we should really take a look at the STK3042 Mark II and see what the pins are. Oftentimes you can kind of get a judgment for it just by looking at the circuitry from the top side. So let me take a quick look, but if I can't figure that out, I'll look up the schematic or the data sheet for the 3042 driver IC and see where the input pins are. What you're really looking for here is a symmetry, and the preamp IC is buried down in here. It's a 4558 op amp, which then should fire into pins, input pins here. And it's going to be a low value capacitor to keep the impedance circuit high. It's going to be like a 1 microfarad or a 10 microfarad, something like that. So far all I see is 33s and stuff. Of course, maybe here we've got a 10, 4.7, 4.7. So really, it's not very clear just by looking at this. So what we can do is get a schematic or get the data sheet and see really what happens. So let's look that up. Okay, so here's the schematic. And you've got your preamp IC here, which then dumps into your tone control network. And it looks like the output of the tone control network looks like it's going to pin 1 and pin 15. Pin 14 looks like a timing, a muting, or something like that, like a bootstrap cap. That's a pretty big value, 33 microfarads. I wouldn't have expected something that high. So 1 and 15 are the signal input. And it looks like pin 8 is the ground for everything. Okay, and see, there's your old output devices there, your STK2030. Cool beans. Alright, so now we know where to go. 1 and 15, that's the easiest. It's the pins on the very left and the very right is the signal input. Okie dokie. Alright, so we'll just make some marks. Pin 1 and 15 are our inputs. Let's just double check and make sure that pin 8 is in fact ground like the schematic suggests. And so let's see, 1, 2, 3, 4, 5, 6, 7, 8. That's 0 ohms. Okay. Alright, now because of having to move the camera and stuff around, I may exclude the part of wiring this up to the board, but the next thing we need to do is focus on the module. The module that we just made up. And what we need to do is attach our leads for our power supply stuff, our leads for our speaker outputs. Oh yeah, I gotta remember that this is the right orientation. So I'm gonna do that. I'm gonna wire all this thing up, mount it in there, and then we're gonna see if the thing works. And that'll be the final part of the video. And I want to kind of expedite this. So I'll show you some shots of everything hooked up and then finally installing it. Alright, so here's everything all wired up. You can see I've got my rail voltages and I've got a common ground which terminates at that black lead there. The teal leads are the speaker. The coaxial is obviously the input, which will go to the pins 1 and 15 of the driver IC. And then we'll link that coax shield to pin 8 for ground for the signal ground. And then we just got to wire up 6 and 15 for the power, 2 for the ground on the main power amp IC. And then we'll pop this thing in, bolt it down, and see if it works. So because I need 2 hands to do that and a lot of room, the next time you'll see this thing, it will be inside the machine. And then we'll fire it up and we'll see what it really does when it's all back together. Alright, so it's the moment of truth now. We got everything back in the machine. Let me turn the fan off. Everything's back in the machine. And here's how it's all wired up. Neat and tidy there. By the way, I discovered that pin 2, which I originally thought was ground, is not true earth ground. Do not use pin 2 for earth ground. Rather, pin 8 on the driver device is a better ground. So as you can see, I've got a little lead sticking up there that I've soldered everything to and made it a ground bus. Pins 1 and 15 are the input pins that go to the new devices. Pin 6 on the output was the negative power supply, and pin 15, I think it was the positive. Yeah, pin 15 and 6. And then the output of the devices, I'm not sure if you can see the little teal lead going there where the emitter resistors used to be. But everything fits. Everything looks pretty good. It's nice and clean looking. There isn't any, since I moved those capacitors underneath the board, there isn't any space constraints. So I've got this thing wired up to the dim bulb tester here, and we've got it plugged in, and we're going to turn it on and see what happens. Watch the bulb. Okay, it briefly flashed and then stopped. Oh, I heard a protection relay fire. Awesome. Alright, so now what let's do, since we've obviously got no excess current draw, let's get my meter, stick it in a chassis spot here, brace it with my solder bit, and let's see. What do we got for voltages here? Plus 33, minus 33. Alright. Yeah, let's go into our speaker terminals here. Speakers A, I've got 0.5 millivolts of offset on the left side, and 0.5 on the right side. It's a little weird, but okay. Wiggling the protection relay does not change that. So, alright. So the next thing to do is let's actually dump a signal into it and put a load on it and see what happens. Alright, so hooked up to a load, no signal, we immediately see that we have a bit of a hum. So what I'm going to do is take my scope probe and we're going to scope out our power supply lines. Let's see if I can turn the sensitivity down just a little bit. Okay, so on the plus side, we've got a little over 500 millivolts peak to peak, which ain't that big of a deal. A little bit less on the negative side. Again, no one gives a shit. That's not big enough to be a concern. Let's check our grounds. Ground looks good. Signal ground looks good. And chassis ground looks okay. Let's see what our power supply is doing. Yeah, 12-volt power supply is good. Got a little bit of ripple, but it's so negligible. Alright, so let's go back to this. It will pass signal. Passes pretty clean signal other than the hum that's there. Let's turn it up a little bit. And we're obviously limited by the light bulb there. That went into protect. Yeah, it doesn't like that sustained overload. Give it more supply voltage, it'll be happy. Okay, but the initial tests show that although we have a bit of a hum, which will work out, the set actually works. So what I need to do, very likely what the issue is a ground loop. That looks like a lack of grounding. I need to check my ground bus and make sure that everything's grounded to the same spot. And then we'll retest. And that'll be the next part of the video. Alright, so after a little experimenting, I discovered that grounding it to the closest point on the physical chassis, which is to that terminal there underneath that screw, yields the least amount of hum. Now we don't have any disgusting hum there anymore. It's nice and clean. Through the headphones I can barely hear anything other than a hiss. And when I turn it up, I get a nice clean signal out of both sides. Lovely. So grounding really is picky on these things. It was like that on the CR440 too. You just got to find the spot that yields the least amount of hum and make sure you ground everything to that common spot. I thought it was going to be pin 8 since it goes there, but for some reason grounding it to pin 8 on the input IC, which reads as earth ground, yields a ground loop hum. So we just went right to the chassis through that piece of hookup wire there. So that does it. It's actually working correctly. Just out of curiosity, let's see what our AC output is. Where can I ground this thing? Excuse me here for just a moment. Alright, so let's turn this thing up. And let's see, let's clip it out and then back off a little bit. This thing was originally supposed to put out 30 watts a channel. And let's see, 1813 on the left side and 1788 on the right. It's a slight difference there. Let's see if we can shore that up with a balance control a little bit. Alright, so that looks equal. So let's see, left side 1774, 1787, that's pretty close. It's about 35 watts per channel. So this thing's doing pretty good. And let's see here. It's heating up a little bit. Not really enough heat sinking for 35 watts. Let's get our little temperature probe here. That's 41, 42, 42. So it's heating up. This probably won't be good for 4 ohm loads, but otherwise it works. So there you go. Once again, we're replacing a hard to get real life STK. Most of them that you get are counterfeit, so these little modules prove to be an inexpensive way to keep your amp going. I hope the video was informative. Just as a recap, grounding is important. We had to kind of experiment with the ground bus before we got rid of the hum. The Mounting is crucial so we get even heat distribution, wiring, all that sort of thing. Make sure it fits in there, obviously. But I hope you guys enjoyed watching the video. I enjoyed putting this together. This is one that'll get saved from the dump. So more stuff to come soon. We're going to get back into that Zenith H845 soon. I've got all the caps I need. I just need to get the tubes, which I'm still rummaging around through my parts supply for. And then we'll get cracking on that one. And hopefully we can find a way to fix the old speaker or get a new one. Anyway, enough rambling. Thanks for watching the video. More stuff to come.